Hi, in the video today we're going to be talking about stereographic projections. In complex analysis, we often want to know about functions that become infinite as a variable approaches a given point. So to discuss this, what we want to do is we want to introduce the extended plane, which is going to be the complex numbers union a single point at infinity. And if you've taken topology, you might be familiar with this concept as it's just a one-point compactification of the plane. And if you're even more familiar with topology, you might remember that this one-point compactification of the plane is actually homeomorphic to the two-sphere in R3. So we want to introduce this extended plane, and then we also want to talk about continuity. So what we're going to do is we're going to introduce a metric or a distance function on C infinity to discuss continuity properties of functions. Now, as stated before, we can represent C infinity as the two-sphere. So we're going to be working with the two-sphere to give us an idea of the stereographic projection. So we're going to label n to be the north pole of the sphere. That is, n is the point 0, 0, 1 in rectangular. And we're going to identify the complex numbers, the complex plane itself, with the plane x1, x2, 0, where x1 and x2 are real numbers, so that the complex plane cuts right through the sphere's equator. Now, for every complex number z, let's draw a straight line through the points n and z. So we're just taking that point in the plane, and we're drawing a line through that and through the North Pole. And that intersection that it has with the sphere, that is not the North Pole, we're going to label it big Z. Now, if our little z has length greater than 1, it's going to be in the northern hemisphere. If its magnitude is less than 1, it's going to be in the southern hemisphere of the sphere. And if it is equal to 1, it's going to lie on the equator. So in this case, big Z is equal to little z. So now let's ask a question regarding limits and infinity. So what happens when we take a complex number z and we approach infinity? What happens to big Z on the sphere? And if you can do this with your own sphere, or you can even do it with a circle and the line. As we go out towards infinity, that point gets further and further up on the circle, and as you get to infinity, you would hit n. You'd hit the North Pole. And it is because of this that we can identify the North Pole n with infinity, and we can represent the extended plane of complex numbers as the sphere itself. Let's dive a little deeper into exploring the representation of a complex number as a point on the sphere. So if we're given a point on the sphere, big Z is x1, x2, x3, and the complex number is x plus I, y. What we want to do is we want to find equations that express the coordinates of big Z. So we want to express x1, x2, and x3 in terms of x and y, the real and imaginary parts of our complex number on the plane. So to do this, let's look at the line in R3 going through the North Pole and the complex number on the plane, so the line NZ. We can write this line in two ways. So the first way we can write it is Tn plus 1 minus Tz, where T ranges over the whole reals. Or we can represent it by the set by breaking it up into its coordinates as 1 minus Tx, 1 minus Ty, and T, where T ranges over the reals again, from negative infinity to infinity. And by doing this, we can actually find z's coordinates. So let's go ahead and label that second representation by 1. So what we want to do to find where z lies on this line, we're going to remember that z is actually a point on the sphere. So what we can do is we can just take the x, y, and z coordinates of our line and square each component and add it and set it equal to 1. Because if a point lies on the sphere, then the first coordinate squared plus the second coordinate squared plus the third coordinate squared is equal to 1. And then all we need to do is solve for t. And we can do that both in terms of x and y, and we can do it in terms of z itself. So writing it all out, we can factor out that 1 minus t squared on the left-hand side and push that t squared over onto the right-hand side. And we get 1 minus t squared times x squared plus y squared. But remember that that is actually the length of the complex number itself squared. So we get 1 minus t squared times the magnitude of z squared is equal to 1 minus t squared. And we can divide both sides by 1 minus t, and we get 1 minus t z squared is equal to 1 plus t. And going through and solving for t, we get that t must be equal to the magnitude of z squared plus 1 over the magnitude of z squared minus 1. Now, plugging this value of t in to our x1, x2, and x3 coordinates, we're going to see that x1 is 2x over the magnitude of z squared plus 1. x2 is going to be 2y over the magnitude of z squared plus 1. And x3 is going to be the magnitude of z squared over 2 minus 1 over the magnitude of z squared. The imaginary part of z is z minus z conjugate over 2. Now let's break this down in terms of z instead of its real and imaginary coordinates. We get that x1 is since z x is the real part of bar over z magnitude of z squared plus 1. x2 is z minus z bar over the magnitude of x squared plus 1. And x3 stays the same. Now, if z is not equal to the North Pole and is given to us, and we want to convert it back to a complex number in the plane, so we just discussed how to convert things from the plane onto the sphere, but now to convert things from the sphere onto the plane, we're just going to set t equal to x3. So we're just going to have our third coordinate be the height. And what we end up getting is the point 1 minus x3x, 1 minus x3y, and x3 as our point on the sphere. Now we know that then we have to have 1 minus x3 times x is 1, and 1 minus x3 times y is x2. So x is x1 over 1 minus x3, y is x2 over 1 minus x3, and so given a big Z, we conclude that little z is going to be x1 plus I x2 over 1 minus x3. Finally, let's talk about distance in the stereographic projection. So the process here is we're going to take the Euclidean metric in R3 for the corresponding points on the sphere to the points on the plane. And then we're going to translate this straight line distance to a geodesic on the sphere. And so if we have two complex numbers in the extended plane, say z and w, they correspond to a big Z and a big W on the sphere. And those are corresponding points on the sphere in R3. So let's label the coordinates for big Z as Z1, Z2, Z3, and the coordinates for big W to be W1, W2, W3. So the distance between Z and W is going to be Z1 minus W1 squared plus Z2 minus W2 squared plus Z3 minus W3 squared. And we're just going to take the square root of all that, just like how we would in a standard Euclidean space. And since Z and W are on the sphere, what we just have gives us that the distance between Z and W squared is going to be 2 minus 2 times the quantity of Z1 W1 plus Z2 W2 plus Z3 W3. Now, using the planar to spherical coordinate change, that would be equation 3 if you want to look back in the video, we get that the distance between Z and W is 2 times the magnitude of Z minus W over the square root of 1 plus Z, magnitude of Z, squared, times 1 plus the magnitude of W squared. And if one of them has infinite magnitude, we can conclude that the distance between Z and infinity, remember that when we talk about distance, it doesn't matter because it's commutative, right? So the distance between Z and infinity is the same as the distance between infinity and Z. So the distance between Z and infinity is going to be 2 over the magnitude of the square root of 1 plus the magnitude of Z squared. And all this correspondence between the points of the sphere and the points on the extended complex plane is the stereographic projection. Thank you for watching. If you have any questions, comments, or concerns, please leave them in the comments below. Thank you very much.